So a lot of people are kind of flipping out. I kind of understand why. Molecular orbital theory is not the most fun process to work with. Right? We kind of go into it and address kind of the basics of it to kind of set us up so that when we move into looking at reactions, we can have a better understanding of why those reactions work. Okay? What's happening with the electronic clouds within them. You will notice if you're looking for the slides real quickly, that picture is not there, but the words are. So this was our big summary out of Chapter 3. So we now have a new way to reference our bond systems. We're looking at either sigma bonds or pi bonds, as opposed to single, double, and triple. You don't want this. So your sigma bonds are your single bonds. The biggest lesson that comes out of that from our molecular orbital theory and our hybridization is that the rotation is irrelevant. Okay? That means we can freely rotate about the sigma bond and we never change the interaction between the orbitals. Well, if the orbitals never change interaction, cool. We maintain the bonds. Nothing changes. The pi bonds, so this is where you're looking at double or triple bonds. Number one, to get that extra bond, we have to put those electrons in a different orbital. Okay? We can't put more electrons into the same orbitals. We have a different way to represent those orbitals. If we push that further, what ends up happening is we cannot rotate about a double bond. The pi bond, being that new system, prevents the rotation, so we end up with a new conclusion, and that was our cis-trans isomerism, right, which we'll again keep coming back to because it becomes more and more important as we evaluate our structures. The next big lesson that comes out of our hybridization theory is increased hybridization. Okay, it means we have more orbitals involved. So if we increase the hybridization, we move to sp3. Okay, versus sp or even s. Okay? As we increase that hybridization, we push our energy for those electrons to higher states. Okay? The higher energy electrons then potentially become more reactive. Okay? So we've got to kind of watch out and be aware of that when we push into looking at the reactivity of a particular molecule. The other big thing that we find is that it becomes less electronegative. So an atom that is sp3 hybridized is less electronegative than an atom that is sp hybridized, which was an important feature when we're looking at our reactivity of our alkanes versus our alkenes versus our alkynes. Okay, so these are big kind of topics that we need to at least recognize and remember when we move into reactions. Okay, will we mention it again when we get into reactions? Absolutely, because undoubtedly you will think that you can forget it. Okay? Don't forget it. Keep it there. So, main way that you would get this question asked on an exam. Get a big structure like this, and you might see some arrows added to it. So let's add in a couple different colored arrows. Number one, let's go there, there, and there. So the first question I might ask is, what is the hybridization of the indicated atoms? So for our first one, that nitrogen. Okay. To figure out our hybridization, what we need to do is look at the groups of electrons around it. And as some of you were starting to jump to already, we have how many groups of electrons? 4, which means I need all 3 of my atomic orbitals. So I generate a new sequence of molecular orbitals, and those are all collectively referred to as the sp3 orbitals. We can now call that nitrogen sp3 hybridized. Okay. What happens when we move to the next carbon over? We look at the groups of electrons. We've got we've got our bond, our double bond, and our 2 sigma bonds. Okay. That one gets a bit tricky because you look at the double bond and say, oh, there's 2 groups of electrons. There are 4 electrons there, but are they independent groups? No, they're still associated with the same 2 atoms. It's one group. 3 groups of electrons means sp2. So what orbitals do we need to hybridize in? The s and 2p orbitals, so that we can get those 3 groups of electrons and their nice little happy stances. All right. Last one at the bottom. Okay. This is a fun one because I'm actually asking 2 questions. I look at it and say, oh, there's only one group of electrons, so of course that has to be s, right? That's the trap. Okay. What do you have to acknowledge? that that atom is a carbon. Carbon must have its octet satisfied unless we have some charge associated with it. If there's only one bond shown, that means there are 3 other bonds to hydrogens. How many groups of electrons? 4. We're now at our sp3 hybrid. Hi. I'm going to erase some of this detail and potentially shift some stuff around to bring up another question. Let's clean some of that up. Our new arrow, I'm going to point to that bond. What question might I ask? Oh, that's a fair question. I didn't think of that. What type of bond? Sigma bond. Single lines, sigma bonds, because single begins with S and sigma begins with S. That's not really true, but it's close enough. Okay, so that works. We've got a single bond there, so we can call that a sigma bond. Okay. That's a valid question, but I would probably scale that up to be a little more difficult. What would I do to make it more difficult?
Can't be rotated.
I don't even want to bring in rotation on that yet, but you're fair. That's a potential question on it. Let's think back to the whole point of this chapter was to look at hybridization. Right, well, we wouldn't look at the hybridization of a bond, we look at the hybridization of an atom. But what I could ask is, what orbitals are making this sigma bond? To answer that question, we need to know what atoms are involved in that bond. And sorry if I sneeze into the microphone or make weird faces in class. Oh. There is something crawling in my nose. Oh. So, which do you know more about, sigma or bond? Bond, fair enough. What do you know about a bond? Oh. Not forces.
It's intra.
We could look at intramolecular. Give me more information about a bond.
2 atoms. 3 electrons. 2 atoms share.
I heard electrons, and in particular, what were you adding? Atoms are sharing electrons. So if I asked what orbitals are involved in this bond, the very first thing that you should be able to tell me would be what atoms are involved in that bond. Right? Don't make it more difficult than you have to. We have a nitrogen and we have a carbon. Okay? To figure out the orbitals, I would then need to evaluate what are the hybridizations of those of those atoms. Nice of me to leave the hybridization information up there, wasn't it? Okay. What was the hybridization of the nitrogen? sp3. So the nitrogen is contributing an sp3 orbital to this bond. What is the carbon contributing? An sp2. I tried, that doesn't seem to work, but it's a nice offer. Okay. Can we scale this up and make it even more difficult? Sure, why not? Let's clear all that information. What's in that bond? We have a sigma bond and a pi bond. Okay. What information can we then add as another layer on top of that?
It's the oxygen and carbon.
We have a carbon bound to our oxygen, and we have a carbon bound to an oxygen. You'll notice that even for the pi bond, I'm showing only a single line. Why? Because a pi bond is only one bond. Okay, so I'm just representing that. When we stack that pi bond with the sigma bond, now we have a double bond. Okay? So what was our hybridization of each of those atoms? Carbon has an sp2. So we could write the sp2 there, and then our natural tendency might be to write the sp2 there. What's the problem with that? The s orbitals are only involved in the sigma bonds. So if I have an sp2 carbon, it cannot contribute to the pi bond. Okay, or that orbital can't contribute to the pi bond. But what's left over if I hybridize one s and two p orbitals? One p orbital. What can contribute to the pi bond? A p orbital. Whoops, that's an eraser. Okay, well, what does that mean the oxygen has to contribute to the pi bond? P orbital. Otherwise, it wouldn't be a pi bond. And we don't even have to go anything beyond that. We can just assume that that has to be true. If we shift over to the sigma bond and explain the hybridization of our oxygen, okay, we now have to go back to our oxygen and say, okay, how many groups of electrons are around it? 1, 2, 3 groups of electrons. The hybridization of our oxygen is sp2. What do we got? sp2. We now have a way to represent the bond characteristics. What orbitals are involved in those bonds, and we can now address some information about them. Okay? If I was going to predict something about the reactivity, which bond would react first, the sigma or the pi? That was an awfully fast response. Why the pi? Okay, now you can't answer because you said pi. You can't answer that question. Somebody else has to.
It's higher in energy.
Why is the pi higher in energy? P orbitals. The p orbitals are necessarily higher than our s orbitals. Right? So if we were going to predict something about the reactivity, we would expect the pi bond to react before the sigma. Is it true? Yes. Awesome. Good. Okay. Those are our big lessons out of this chapter. I know there's a lot of other questions in the homework about all sorts of different applications and how do you draw all these things. Yes, that gets a bit tedious to work with and kind of work and struggle through. We want kind of the basal level, and we'll keep coming back to it and reviewing that information when it becomes more relevant for each of those bond structures. Okay? Questions? Oh, so let's get there. We already talked about this being my favorite section, looking at nomenclature. Our primary focus is what can these structures do? What's their reactivity? What's their interactions? All of that fun stuff. You are ultimately responsible for being able to name these things, so you have to have at least a basal level for nomenclature. Okay? What we've got on this slide is a ridiculous amount of information that as I talk and work through more nomenclature problems, I think I need to add a little bit more. But ideally what I'm trying to do on this slide is put everything that you absolutely must know for nomenclature on one slide. Okay? And a lot of people have asked, well, the textbook isn't referencing the rule used to name this compound. Fair enough. Okay, so where do you find the rules to name your compounds? Okay, it comes from IUPAC. Okay, IUPAC. They decided all the rules for naming organic compounds. Why does your textbook not list all the rules that IUPAC went through and listed and gave you perfect examples of? Because the rules that IUPAC has put together is equivalent in size to your textbook. Okay?
Oh my gosh.
If you add that into it, your textbook now triples in price, okay, and triples in breaking your back. Okay? So a lot of the rules that get addressed and you see pop up, it is a bit unfortunate that your textbook doesn't always list the perfect rules for it. That's something I've noticed that all textbooks seems to mess up on. Okay? They will provide you examples. Oh, yeah, I know how to name this compound because I've been working with the compound for 50 years. Of course I know how to name it, but I'm not going to tell anybody the rules on how to name it. Okay? All of the textbooks will make that mistake. Kind of watch out for it, see what you can do. Do the best you can within nomenclature. Primary things to focus on: number of carbons. Meth, eth, prop, but, pent, hex are the absolute, as soon as you hear hex, it's 6. Okay? There's not even a translation moment. That's immediate. Hept, oct, non, dec, undec, dodec, whatever you want to go after dec. Okay? Those can be kind of a slower response because you don't see those quite as frequently. They do show up, just not very often. Okay? So 1 through 6, you need to know those prefixes. And those are in reference to how many carbons are in the longest carbon chain. So we've got kind of our rule set. And when we draw a chain, what's the problem with the chain? There are 2 points on a chain. Well, if you number left to right, is that different from numbering right to left? Yeah. Okay. Unfortunately, that's a really big difference. So how do you know where to start your numbering? Well, there's a rule for that. Okay. If you don't know that rule, you're wrong, unfortunately. So your rule typically goes at starting at the highest priority. And by highest priority, we're looking at our functional groups. Okay. So all of our common functional groups are listed in that priority chart. Okay. Starting all the way up with acids, and you work all the way down to halides. So depending on what functional groups are present, you will name according to those kind of subcategories. Okay? Then you've got to go through and specify how many or what your primary functional group is in your structure. You've got that to tack on. You've got to specify the location for each of your substituents, where all those other functional groups are. And then you've got to organize all of those individual substituents in the proper order, and that has to go alphabetical. Okay, so you've got all these kind of weird, crazy things that you have to combine. It gets exceedingly frustrating for a student starting in organic chemistry. By the end of organic chemistry, you will be begging for nomenclature questions because you'll understand nomenclature so well that you'll find all of it easy, theoretically. Okay? Where we start is relatively simple. We look at just the alkane and the halides. And then we start to scale it up and add in different functional groups. Again, theoretically, by the end of the semester, you could have a structure that has every single one of those functional groups in the structure, and you have to be able to appropriately name it. Okay? Theoretically. So, alkanes, general patterns for our alkanes, our alkenes, our alkynes, and even our aromatics. So we're looking at just carbon and hydrogen structures. Our alkanes have the general form, which we've talked about already, Cn, where n is any number or any integer, 1 or bigger. And then hydrogen is twice that plus 2. If you have that pattern, okay, there are no double bonds and there are no rings. Right? It is a fully saturated structure. Every pi bond or every ring loses 2 hydrogens. Okay, so you could go through and prove that to yourself with each of the alkenes or alkynes or aromatics. As far as your general properties go, what we would do is look at the bond nature. Well, what types of bonds do we have in alkane? Lots of different answers. Single bond works. Also not particularly helpful, so try again. What else do we have? I'm hearing sigma, also very true, also not very helpful. Where do we start everything off with? We didn't talk about orbitals or sigma or even single. What did we start with? Lewis, and deciding ionic, polar covalent, nonpolar covalent. What type of bond do we have in our alkanes? Nonpolar covalent, which leads us to what type of force? London dispersion forces. Now that we have our force, we can predict something about its properties. Well, what are its properties? Boiling points we would expect to be very, very low because we have very weak forces. Okay? So it's those combinations and those evaluations going all the way back to the stuff we started with and slowly processing forward. As far as our formula versus structure, you will almost always see things written out in your Lewis, not your Lewis, in your line angle. Okay? You might see some VSEPR information drawn in there, but the only time VSEPR becomes important is when you move really into Chapter 5. Okay? You might also see this thing known as a condensed formula. Okay? Particularly frustrating, because if we look at the condensed formula for our alkene, it becomes... Why is that a particularly frustrating formula? Where in that formula does it say there's a double bond? It doesn't. We remove that information when we look at our formulas. Okay? You are responsible for interpreting formulas. That's why you will see formula things pop up, okay, or those condensed formulas. Get used to working with that and trying to come up with those formulas and draw those structures. It is going to be incredibly important to get to the structure, because the structure is where your chemistry is located. Butanes. Okay. So what I want you to do is go through and draw the Lewis structure for C4H10. Feel free to go through and draw that out. Make sure it has that formula, but you can draw it any goofy way you want. How many of you have this kind of thing being drawn on your paper? Something like this. I'd say yes. Okay? Wrong. I didn't ask you to draw that. I wanted you to draw this. How many of you drew this? Does that match the formula? For all that work, you went through and drew it all out, and you still drew it wrong? Why is that? Okay. Formulas are pretty useless. So one of the things that we'll look at is not drawing formulas, but drawing the structure, or at least adding something into our formula so that we can understand what's happening with our structure. So how could we, or how could I ask this question a little bit better and allowed you to get to this answer and be then, oh, of course, everybody got it right. Well, I've got CH3s. How many of them do I have? All bound to a carbon with a hydrogen. There's our condensed formula. That gives us that information. Right? So there are a variety of ways that you can look at formulas. Ultimately, the condensed formula is where you've got to bring in that interpretation. That's where you're primarily responsible. I will never ask you, provide the formula for C4H10, and if you provide me a straight chain C4H10, should have, yeah, 10, that was right, I would not say you were wrong if you drew that, okay, on an exam. Okay, the question would be too vague for you to be able to go through and predict. So the reason behind this is that we don't have that clear information. So we now need to look at what is the relationship between these structures. Okay, are they the same? Well, they have the same formula. Does that not make them the same? Okay. If we think about their properties. Oh, I don't want to crumple that up. Where's that stack of papers? Sorry, Dr. Bates. If we take our butane structure and we look at its interactions, it's relatively flat. Show that interaction over the top. What prevents me from pulling these two pieces of paper apart? It's the friction between the two pieces of paper. This is why I'm apologizing. What's the force that keeps these two pieces of paper now connected? Smaller or larger than the previous? Much smaller. Does shape have an effect on the intermolecular forces? Yes. If we take a look at these two structures, the one on the right is effectively the balled up piece of paper. What is that going to do to its boiling point? It's going to lower it. Right? So looking at that structure drastically changes how it can interact with its environment. Okay? Both with just physical properties or melting points, but it can also lead to different functional groups if we bring in a different atom. So we have to be very careful when we look at our formulas to make sure that we're drawing the actual structure that we want. So as far as this relationship goes, they cannot be identical to each other. Because if they were identical, they would have the same melting points and boiling points. Okay? So there's something else going on here. What these end up getting referred to is some new classifications. Okay? They aren't officially different from each other because they're the same number of carbons and hydrogens. So we've got these three ways that we can change our words. Okay? You've seen this before in chemistry. For instance, spontaneous combustion means what? Okay, so if someone spontaneously combusted right now in this class, would everybody panic? Okay, most people are laughing. Oh yeah, someone just blew up in flames? That would be insane. Guess what? You're all spontaneously combusting right now according to a chemist. What is the chemistry definition for spontaneous? It's the difference in energy between your reactants and products. Okay? We are already combustion, hence breathing. What do we exhale? CO2, the product of a combustion reaction. Just because we have some preconceived definition of what we think same or identical means does not mean that translates into chemistry. So when we look at these, we get different, identical, and isomers. Different are a little bit straightforward because our formulas are entirely different from each other. We've got different atoms in there. So those won't, or that definition kind of holds. Identical is where it gets tricky. We have to have the same formula, and the structures have to superimpose. This also gets a bit odd because what we're doing by superimposing means that we take those two structures and we completely overlay them. So if I take my hands, are my hands superimposable? cut my thumb off? Not quite, then my pinky still doesn't overlap. So one natural response to most people, oh, right here. Don't those superimpose? Is the top of my hand superimposing with the top of my hand when I clap them over? No. Okay. Superimposing means that we have to match exactly over the top. Okay. The other option is superposable. You'll hear these two words. They are used interchangeably, okay, at least by me. One means that we just kind of stagger them and you can see that they would overlap. One means they literally occupy the exact same space. You've pushed them over so that they are identical in the exact same space. Okay. It's a little bit of an odd discrepancy. Don't stress too much on it. The other definition is isomers. Okay. We have the same molecular formula, but the structures do not superimpose. So my hands would be identified as isomers. They're not different because I have the same number of fingers and thumbs, thankfully. Okay. They aren't identical because I can't superimpose them. So my hands are isomers. Okay. Structures are going to have a very similar issue with this. Okay. So we can look at classifying any two molecules, okay, based on these rules, okay, based on those definitions. Molecular formula, superimposable, and connectivity. That connectivity brings in another tier to this. Move into chapter 5, and what happens? We get yet another tier on top of this. Okay? And we have to come up with a relationship between any two structures. How are they interrelated? Well, why is that important? If we take a look, oh, it's nice and up in the top of the screen where you can't see it, so let's draw it again here. If you've already had lab, do not answer this question, please. What is the relationship between these two structures? We bust out our formulas. We've got how many carbons? 4. How many hydrogens? Should have, is it 10? Yeah. I can't do math. 3, 6, yeah, we got 10. The other one is C4H10. Cool. Well, can I superimpose these? If I slide that one structure over on top of the other, does it match? Okay, no, it doesn't. So we say, oh, they're isomers. Yeah, we got a problem with that. What's that problem?
You can rotate on a sigma.
What bonds do we have in each of these structures? Sigma bonds. What does a sigma bond do? Rotates. If I rotate about that sigma bond, is it now superimposable? Yes. What's the relationship? Identical. So whatever we decide to draw may lead us to vastly different conclusions. So when we make a drawing, we have to remember sigma bonds can rotate, pi bonds cannot. In those relationships, does that change how I interpret the structures? Okay, and determine those relationships. So you have to be very, very good at manipulating the rotations about each of those lines. How do you become that good at it? Don't ask me, I didn't do it. Years and years of practice. Okay? The other way to do it, model kits. Okay? The model kits are there to help you visualize and see those three-dimensional representations. Okay? Which is fantastic. Everybody loves model kits. Okay? Or at least everybody should love model kits. Again, one of the reasons why I push model kits is to help with this three-dimensional representation. And we take it a step further. Most students say, well, I don't need it because somebody else said they didn't need it. They also didn't do as well as they should have in organic chemistry. Okay? Or they're one of the 10% of the population that is phenomenal at seeing things in 3 dimensions. Okay? So there is probably 1 to 2 of you in this class that has a phenomenally awesome brain that can deal with these 2-dimensional drawings and flip those into 3 dimensions, do all that spin, flip, and rotate and stuff in your head. And to you, you are a horrible person. Okay? I cannot do it. I've never been able to do it. I have to use the models. Okay? So chapter 5 is even more embarrassing for me because what you'll see when we deal with those is it becomes even more difficult to see these relationships, and I will draw it again and again and again. And some smart aleck kid comes, well, didn't you just rotate that? Yeah, I rotated it and I had to draw it to see it. Okay? Draw it out. Okay? It will help you. So, back to our kind of name. How do we process and deal with these things? Okay, so we got a lot of color coding going on in here. And I need to tag in here. I'm not sure how I can write this in a different color. I guess I'll just have to go black. We got shape written in there in a color that didn't show up. The only place that that is really showing up is in that second example. Okay, so if we go through and try and draw these structures, we're going to go from the structure, from the name to the structure. We would need to break down all of that information that's stashed in that name and turn it into a structure. Okay, well, how should we start this? Where do you start most things, being an English language student? Left to right. Okay. You're fine if you want to go through and do that. I would argue that's not the best place to start. Okay, so then people go, oh, well, you start from right to left. Also, if you're used to that, fine, go ahead and stick with that. Where I'm going to start, right smack dab in the middle of this. I'm going to start with that hex. What does that hex mean? 6 carbons. So if we go up to our color coding, that's our number of carbons. So I need 6 carbons. So what I'm going to do is draw 6 carbons. You'll notice that when I draw 6 carbons, I immediately jump to using the line angle format. I should have 2, 4, 6 carbons. The next part that I would jump to would be that ane, or that AN ending. That AN ending signifies that I'm looking at an alkane. All of my carbons are singly bonded to each other. Okay, no double bonds, no triple bonds. So the drawing that I've got is just single bonds. It's okay, you can laugh. What's the E for? The E would be where we would draw in our functional group. Well, in this case, we don't have anything fancier than just an alkane. So we end with just the E. There is no other fancy functional group, so we just end it with the E. So what I've now done is combined everything in my little drawing, and all I've got is this hexane aspect. Okay. Where do I move to now? Okay, we want to move to the substituent. The substituent has a bunch of information associated with it, okay? And oddly, incorrectly, information associated with it, which we'll address. I have a location, I have an amount, and I have what the substituent is. Where should we start? Okay. Again, it's personal preference. I would start with what it is. What is the substituent? It's a methyl. What is methyl? 1 carbon. So I have a 1 carbon located at position 3. Where's position 3 on my structure? There we go. I was waiting for you guys to tell me left to right, and I was going to be right to left. Okay, it doesn't matter. Okay, most people will go left to right. I will say that a common tactic on exams, particularly to standardized exams, is to not number left to right, because that's how you naturally number. So they tend to number things the other direction. And now you flip out and think it's a new question. Okay? So let's go through and do the flip out method. I'll go through and number, and I'm saying 1, 2, 3. At that 3rd carbon, I have a methyl. You'll notice I'm not drawing CH3. Why am I not drawing CH3? It's just a 1 carbon. I can imply that that's a carbon, and it's got 3 hydrogens. I don't need to specify a CH3 there. It's already implied. We now run into the issue with this name. Okay, at position 3, I have a methyl. That's what the name suggests, right? But it also says di. That means what? There are 2 methyl groups. Where's that other methyl group? Okay. This is the problem with the name. You must specify the location of every single substituent. So based on the information we have, where does that other methyl go? Where did our first methyl group go? Position 3. So that 3 is now taken care of. Where does our second methyl group go? It's not supposed to be anything. Okay? There is no identifier on where it belongs. Without that identification information, we have no idea where it belongs. Okay? What needs to be adjusted in our name to make sure that we know where it belongs? Now where does the methyl group go? On our third carbon. There's our other CH3. Okay? You'll notice that we do not change the numbering scheme. It still stays the same. So even though I have two methyl groups located at the exact same position, I must specify the location for every single substituent. So if there are two methyls at position 3, I need to say 3,3. Okay? How do I separate that it's not position 33? And don't tell me because there's not 33 carbons in hexane. We just add the comma. Okay? Without the comma, now we don't know. We wouldn't know if it was 33 or maybe it was 3 space 3. Okay? Which makes this even more challenging when it comes to nomenclature. If you don't include the comma, what happens? It becomes 33 and it's wrong. What if you don't include the dash? Can you tell a difference between the 3 and the D for dimethyl? You know, relatively standard. We could see those apart from each other, right? Still wrong. Why do you need a dash? Every time you have a letter to number interchange, you need a dash. Next part of this. Why was there not a space in there between the dimethyl and the hexane? Because that guy in IUPAC sat down and said, there is no space. This is the law. Okay? If you put a space in there, what happens? You're wrong. Okay? You have to follow the rules very, very strictly when applying and putting together your names. Okay? And unfortunately, you'll see that sometimes there's variation off of these. We kind of have to just deal with that as it comes. If we move to the next one, I did it again. Let's fix that next one. Let's call it 3 again. Actually, I can't call it 3. Got to call it 1. We'll talk about that in a second, too. How would we go through and draw this structure? We got 6 carbons again. Okay, but we've got a little bit of an issue here. It's not just 6 carbons. That cyclo means cyclic, which means ring. I have to put 6 carbons into a ring. Okay, well, for the uninitiated, it gets a little bit tedious. You might go 1, 2, 3, 4, 5. Oh man, 6. Okay, and you get this weird, odd shape. Okay, as you build up practice, you'll realize that you're looking at a hexagon, and you'll draw those out a lot faster. Okay, now that we've got our cyclo and our 6 carbons, we know it's an alkane, so all single bonds because of the AN ending. Okay. Next part is we have what substituent? A methyl. Your first substituent on a ring always goes to one position. And that was not intended to be ironic, but it actually worked out that way. Where's carbon 1 in a ring? Where's carbon 1 in a line structure? The beginning or the end? Where's the beginning or the end in a ring? There isn't one. So guess where carbon 1 is? Wherever you say it is, that's where it starts. Your first substituent, if there's only one substituent, goes to position 1, which is wherever you want it to be. Okay? That's why I ended up saying that we had to write 1, 3. Okay? We couldn't have said 3, 3. So if I said 3, 3, then I'm saying the methyl groups are located position 3 for both of them, which doesn't make sense for our name. Okay? So our first methyl group is at position 1. Where's our second methyl group? Position 3. So if we go through and number, position 1, right here. Where's position 2, up or down? Oh man, you had to say wherever, didn't you? Doesn't matter the numbering system. As long as we're consistent with it, we should be okay. Now that we're position 3, what do we need? Another methyl group. Okay. Take a swing at that last one. Okay, it is a little bit harder. Technically, that's looking at a functional group that we'll talk about at the very end of the semester. But you should still be able to get it if you happen to remember all your rules, okay, or if you have the PowerPoint slides in front of you. So if you got a question, raise your hand. I'll come to you. With this structure, we've got, what did we said it was 3,3, right? We should start with our hex, which gives us how many carbons? 6 carbons. You'll notice I tend to like 6 carbons. I draw that a lot. It gives me enough to actually do stuff with. So we got our 6 carbons. We've got the ane, which means all of the carbon connections are single bonds. And interesting extra piece of information. We have a new functional group. That functional group changed our ending. We no longer have that E ending that we saw in all the others. It's now switched to an all. What did the all mean? An alcohol, which brings up the next question. Now that you know it's an alcohol, what does an alcohol look like? It's an OH. How do you know that? Because back at the beginning when I said these are the functional groups, you should know all these functional groups and what those structures look like. And I said you should nail that down in your head. If you haven't done that, you may know it's an alcohol. That's pretty useless information until you can draw it. Right? So it's an alcohol, which means we have an OH. The next question is, where does that OH go? So this is where we can potentially see these numbers pop up. You may see that number pop up immediately in front of your functional group. That is saying that our functional group is located at position 2. So at position 2, I need to add an OH. Right. Now what? Now we've got our methyl groups, which means 1 carbon. Where are those carbons located? The 3rd position. I should have a CH3. Let's go ahead and just draw that in just for the heck of it. Why not? It says dimethyl. Where's that 2nd methyl located? Also at that 3rd position. Okay. So we've got our names to our structures. Sorry, man, I always screw that up. What's up?
Dimethylhexanol, or do you say 2?
Careful. So if you say dimethylhexanol, have you specified where the alcohol is? No. Did you actually specify where the methyl groups were? No. So if we say the name for this, it is 3,3-dimethylhexan-2-ol.
That sounds like a bad joke.
Sounds like a bad joke. Or a bad dream. It's even better. Sorry, Troy, and then Michael. What's up, Troy?
It's hexan.
Hexan.
Why is it?
An as in A-N, because it's all single bonds. Not hexen, hexan, 2-ol.
With the E at the end would mean
That there's no alcohol.
no alcohol.
Yeah, if we put that E there, we can't have the alcohol.
So it ends in
It would end that structure. Not an amine, an alkane. Just single bond, carbon and hydrogens, no other functional groups. Just a sec. Right? You can have more than one functional group on the same structure. So if we had a bunch of functional groups that were high priority, we end up having to pick out where we put them. Okay? When we'll cross that bridge when we get there. Yes.
So the E is just all the way down. That's where it stops.
That's the end of the name. Yeah. The E is just kind of a way to finalize it so that it's not, so it makes it a hard A. Is that what E ending at the end means? Something like that? Something from English? I don't know. Okay? So, the other option is going from your structure to your name. These become tricky as well, because in our very first step, we have to find the longest carbon chain. Why does this become dangerous? Well, if I go through and look at this first structure, I can go through and say, well, I see a long carbon chain right there. There's 3 carbons. Well, there's 4 carbons there. Well, there's 2 carbons there. Which is my longest carbon chain?
The green path.
None of those.
Wow.
Okay. My longest carbon chain starts with that first carbon, 2nd, 3rd, 4th, 5th, 6th, 7th. Okay. Is there another way we could have labeled that? Well, if we look to the far right of that, we've got 1, 2, 3, 4, 5, 6, 7. Uh-oh. So number 1, what's our longest carbon chain? 7. So our center of our name needs to be hept. Okay. What's the ending going to be after that? So we're going to go with hept. We got the AN. Do we have any other functional groups? Cap it off with a nice little E. Okay. The next part of this is, okay, well, how do we decide which of these chains is the more appropriate one to use? Okay, well, this comes back to nomenclature. Someone sat down and decided the way we want to go through and name these is to give us the maximum amount of possible junk we could have attached to our main chain. So what do I mean by that? If we look at that first example, I've got 1 piece, 2 piece, 3 pieces versus 1, 2, 3, 4. And that second highlightation of my chain, I have more pieces attached. Well, someone decided that more pieces is more better. That's the proper chain to highlight. That means that's the one I need to look at, not this other one. How is that obvious to you as a student trying to do this problem? It's not. How do you figure it out? You try all possible options until you get the correct one. Right? It's one of the common frustrations that organic students have. You mean I've got to do it 6 different ways? Yeah. Suck it up and do it. Okay? If you try and just jump straight to the answer, you will find that you will find the wrong structure. Okay? There are multiple ways that we can find chains within this, and we could still come up with a name that matched all the other rules, but it doesn't match that first rule. Okay? It has to match all of those rules. Yes?
The last page 3, could you, instead of going straight down, could you go to the right? I mean, it seems like that's the same.
As another option, let's see if I can do it in orange. We could have just as easily shifted that direction. Is that going to change any of the bonding orientations of anything? No, it's going to be exactly the same. So because it's exactly the same, oh, that was the wrong button. We don't need to worry about it because it's exactly the same, so we don't need to stress. Right? So one of the first things that I would go through and do is find that longest carbon chain. Since it's in green, we'll go through and do that, and I would circle that. I've now identified my main chain, and that's now locked in position. And when I write out my hept ane, it is now defined, and I don't worry about anything else. So now what do I have to do? I would argue you don't even need to worry about direction yet. This is one of those skills that I picked up as hating nomenclature.
Really start from top to bottom. Remember, we have different.
What are the substituents? Okay. I got 1, 2, 3, and that. I could name these. I've got methyl, 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 and ethyl. Why did I name each of those 3 methyls? Because this is going to remind me not the tri, because you guys probably already picked up the tri, but what is it going to remind me? I need to provide the location for every single one of those. Okay? So now that I've got my substituents, I need to go through and look at that and decide which way is best to number. Top to bottom or bottom to top? So to the doesn't matter, sorry, yes it does, this is nomenclature. There is a correct way. Why bottom to top? You want the lowest possible numbers for your substituents. Why? Somebody said that's the way to do it. You now have to do it. Okay? There isn't some grander scheme of what works and why it comes out that way. It's somebody said this is it, so you have to do it that way. So if we start numbering from the bottom, it can help to go through and actually drop the numbers in. 1, 2, 3, 4, 5, 6, 7. Where's my first methyl located? 2. Where do I write that 2?
The beginning.
I'm going to write it right next to my methyl. What's the next substituent I encounter? 3 with the ethyl, then 4 with a methyl, then 5 with a methyl. Probably the worst time to share this, but we'll go ahead and do it anyway. Your final exam is what? The ACS test, which has what questions in it? They're standardized multiple choice questions. I would argue at this point I have all the information I need. I do not need to take it any further. I can use my multiple choice answers and eliminate the crap out of the exam and get my answer. Right? Because now the question is, how do I take all of this separate information and officially drop it into a name? Okay, well, I just have all the pieces. Does it matter how I put the pieces together? Son of a, yeah, we got to put it back together in the right method. Right? So you have to address that next issue. Okay? So when we drop it into the name, what do we start with? Do we start with the methyl or do we start with the ethyl?
Is it alphabetical order?
What's our rule? Alphabetical order. So the first thing that shows up is our 3 ethyl. Okay, we got the 3 dash, there's our ethyl. So now what's the next thing that needs to show up? Oh, you snuck right out of it. We need a dash. Why do we need a dash? Because now to bring in the next substituent, I have to specify those locations. Okay. Why do I say 2, 4, 5, not 5, 4, 2, or 4, 5, 2? We're just trying to put them in the most lowest to highest numbering. Now what? Dash. Try for the amount of them. Methyl. No space. Heptane. Yes. Okay. So it's a question of approaching all of these rules and slowly hitting each and every single one to get through to your final name. It almost always it will only show up as multiple choice. Okay? I will never ask you to spell out the name. The primary reason being, if you leave out a space or you put in a space, how many points should I take off?
None.
It's technically wrong. What if you forgot the dash? Okay. There's now so many different ways to approach trying to take points out of it. It becomes a nightmare to grade. So it becomes either all or nothing. If I'm going to do it all or nothing, I'm just going to make it multiple choice. Okay? So that's where you'll be primarily concerned about nomenclature, at least going from the structure to the name. Name to structure is a whole different animal. Okay? That you have to follow the same patterns. You should always come up with the structure appropriately. Okay? Most people seem to be able to go from the name to the structure relatively easily. Where that becomes challenging on a multiple choice exam is maybe the way they chose to show that structure looks different than how you drew it out. That goes back to that whole butane question of, was it zigzagged or was it kind of U-shaped? Okay? So you would have to evaluate that structure, evaluate all those single bond rotations, and try and match it up within those multiple choice. Okay? Yet another tier of fun stuff on top of this. You will notice that as you also continue through that we don't use just the IUPAC names. Why? That's because some old guy came down and said, I've always called it acetone. I'm not calling it 2-propanone. Not going to do it. Okay, so it's called acetone. Everybody now has to listen to that old guy. Okay? So you will see common names also show up. Okay? You're less responsible for those, but they do occasionally rear their head. And it's usually with this isopropyl functional group is where it shows up, is the iso. Okay? With one carbon, you can only have one way to arrange those atoms. Same deal with 2 carbons. They have to be in a chain. As soon as we hit to 3 carbons, there's multiple ways we can arrange those carbons around a main substituent, and we get 2 different possible combinations. We get the straight chain form, and we get this kind of bent form. Well, what happens if you add a fourth carbon? You get even more ways that you could possibly arrange it, which is that whole bottom section. Okay? There is some pseudo logic behind those. It is very pseudo, but it is there. Iso is in reference to the shape right here. That shape is an iso shape. Okay? How many carbons are in this shape? 3, so we'll call that isopropyl. Take a look at your 4-carbon sequence. Do you see isobutyl pop up? Yep, where's that shape? There's that shape, except I've added 1 extra carbon before it makes it to my substituent. I now have isobutyl. What would isopentyl look like? CH2, CH2, there's isopentyl. There's again the iso shape, but now in the total substituent, I have 5 carbons.
So iso always has the CH3, 2 groups of CH3 attached to just the CH?
Attached to just a CH, yes. Yeah? No. Okay. So the question there was, is it always facing that way? Okay, the fun example I'll always come back to is, what's my name? Really? Come on now. What's my name? Thank you. What's my name now? Our structures are free to rotate, flip, and move wherever which way they go. The name does not change. Okay? When we move into the butyl, okay, you'll see an extra term potentially show up. You saw it show up actually with the propyl. That N stands for normal, which means straight chain. Okay? We got the iso, but then you see the sec butyl and that tert butyl. Sec is in reference to that carbon being connected to 2 other carbons, or secondary, so hence sec butyl. What if it was sec pentyl? Add an extra carbon on that chain, okay, the longer chain. Tert butyl stands for tertiary, meaning that there are 3 carbons coming off of that. These are your most common name structures that you've got to watch out for. Okay? Super exciting. Rings. Rings typically take priority because there's a lot of carbons in them. But if for some reason something's attached to the ring that has a higher priority, like there's more carbon, it's a longer carbon chain than that's in the ring, you would name the chain and the ring as a substituent. Okay? To be named as a substituent, is it on this one? I think it's on the first one. Your substituents pick up the YL ending, okay, which we already kind of looked at. With our meth-ol, that YL said that it was a substituent on our primary structure. Okay? One thing that we addressed with our rings as well, if we looked at cyclopropane, how many carbons? 3 for prop. There's our 3 carbons. Where's our first substituent go? Sort of. So let's go ahead and put it there. What's the name of this compound? So there's a methyl. It's a cyclopropane. I heard, oh geez, you know what I've written out there. Okay. I heard someone say 1. Do I need to specify the 1? Not necessarily. It's implied because the first substituent is located always at position 1. Is it wrong to include it? You definitely hit a gray area. Okay? It shouldn't be marked wrong, but sometimes it does. Okay? Oh, I'm really sick and tired of nomenclature. Can we say we're done with it? Not to like influence your decision or anything. I'll do one more example if you want one more example. I will attempt to keep the trivial names off the exam as much as I can. This first exam, I'm pretty sure I can keep them off entirely. The other exams, because it does tend to show up, will show up eventually. Okay? So let's actually, just because you mentioned the trivial names, let's take a look at an example here real quickly. We picked this guy. What will we name this compound? We got our longest chain being 7 carbons. I was nice, did it in a straight line. So we got a heptane. At our 1, 2, 3, 4 position, we have. So if we circle our main chain, how many? What's our substituent?
Propane.
It's not propane because it's not a straight chain. So I'm hearing a lot of people say isopropyl, which is interesting, considering the question that we just answered was, do we have to know the common names? Well, one of the names for this is 4-isopropyl heptane. Pretty straightforward name, not too bad. But that's not IUPAC. That's a common name. So how do we name it in the IUPAC fashion? It is still heptane, but I can't call it isopropyl. So what I go through and do is say, what is the longest carbon chain of my substituent? 2 carbons. Carbon 1 being the location where it's attached to my main chain. So carbon 1, carbon 2. What is the name of a 2-carbon chain? Ethyl. What is the substituent on my substituent? Where is that substituent located? 1-methyl ethyl. Why does this become a challenge?
So it's 4,1-methyl.
String this guy out here. We got to specify our location. 4-1-methyl ethyl. No spaces, remember.
Do you have to put the common?
What's the connection between the 4 and the 1?
Usually.
We drop the parentheses to separate the 1 away from it. Okay? The second example is our official IUPAC name. So you'll find that it is often easier to name using our trivial names. Okay? Hence, we use the trivial or common names. Okay? So when it comes to nomenclature, it's practice. Working at it to figure out the rules and trying to process through it. We're looking for those main pieces. Okay? How many carbons are in your carbon chain? Okay? Where are your substituents located? Naming those substituents. Okay? Finding the longest carbon chain. All of that just takes practice to go through and build and pick it up and kind of learn with it. You may see in your homework or on the exam kind of an imbalance between using the common name and the IUPAC name. I will try my best to maintain it in the IUPAC fashion. But as we just saw, it's not particularly fun to deal with the strictly IUPAC fashion. Yes?
How come you put the methyl first in that instance because it's the substituent?
It's the substituent on our substituent,
If
yes.
they're both the same substituents of heptane, then they would be.
Then you'd swap it, yeah. Okay. The other thing addressed in nomenclature 1 is that our other functional groups, we have halogens, nitros, and alkoxes. Okay, so these are now just names that we have to do for or the names of those pieces. So if we have a halogen and it's a fluorine, we call it fluoro. If it's a chlorine, chloro. Bromine, bromo. Iodine, iodo. Treat it the exact same as you would any other substituent. If you see a nitro group, okay, or the nitro term come up, what that is in reference to is actually this functional group, where we have a nitrogen doubly bonded to one oxygen, singly bonded to another, and then to our main chain. That is a nitro associated with it because, is that an appropriate Lewis structure? The nitrogen is positive and our oxygen is negative. Okay, so if you see that, you're just using it as a nitro, use it the same way you would your halogens. The next one is your alkoxes. I'm not going to get anything through nomenclature or finish with the next section. What if we have an RO group, so some carbon connected to an oxygen? That gets named as an alkoxy, is your substituent name. The alk in reference to carbons. The oxy in reference to the oxygen. Why do we call it alkoxy? Because we're trying to be generic about it. If it's only one carbon, we don't want to call it alkoxy. We want to be specific and say that it is only one carbon. How do we say that? Meth oxy. If it's two carbons, eth oxy. Okay? So we would then use that to go through and process our names and locate where everything is. Okay? So treat those as you would any other substituent. You're just now adding a new name for it, or a new piece. Okay? I'll leave that to relegate to the textbook because you can see common names pop up. You'll see them show up in lecture, or not lecture, in lab. You've already seen methylene chloride pop up. That doesn't make sense as far as your IUPAC name, because according to IUPAC, we end with our carbon chain. Well, methylene chloride ends with chlorine, not carbon. Why? It's a common name reference for that structure. If you really want to get into it, I can talk to you about the methylene thing. It's just obnoxious. So what do we do for the exam as far as Chapter 4 goes? Well, I got a minute and maybe 10 slides, so it won't be too bad. I think I can do it roughly 10 seconds a slide. So to start, with methane. We got methane with our general tetrahedral shape. And we got all those bonds, wedges, and dashes coming off of that. And we could specify all that extra information. Okay, so if we built the model, we could see that, we could draw it, we'd be happy with it. But what happens if we change our view of the model? Okay, so, and I'm kind of kidding about that. Did I do the example for our tetrahedral shape, right?
Yeah.
Okay, that and that. And we got a reasonable tetrahedral shape. My hands and my body are in the plane. But what happens if we change your viewpoint? And since there's people sitting close to me, I can't do it. What if I lay down on top of a table? What atoms are in the same plane? And let's change it again. What atoms are in the plane of the paper that you would be using for our whiteboard? Try again. None of them are. My hands would be coming at you. My legs would be going away from you. Is that a valid interpretation of the model? Absolutely. Would that make our drawing look awful? Yeah, absolutely. But would we ever shift to looking at it like that? Any of you interested in biochemistry, biology, that kind of fun stuff? Oh, I know you're more excited than that. Come on, really? Everybody's going to chemistry, organic chemistry. You're all going to biology, aren't you? Guess where this viewpoint shows up? Biology. It's known as a Fisher projection. Okay. The other viewpoint that will show up in our textbook is something referenced as a Newman projection. I will keep it relatively simple when it gets to it. You will be doing stuff in the lab with it, so it gets a little bit weird, but if we take a look at our ethane molecule and we rotate about the sigma bond, it sure doesn't look like anything's changing until you turn on it and look out on its side. Now does it change? Yes. That is your Newman projection. We will ask some questions on the exam about that, but keep it relatively limited. We will pick up there. I apologize for running a couple minutes late. Pick up there after exam 1, finish up our chapter 4, then move into chapter 5. After exam 1, please keep packing up. No, I'm actually serious. Please keep packing up.